All right, ladies and gentlemen. Yeah, thank you very much. Very good morning to all of you, and welcome to the fourth day of the sixth edition of Students' Talks on Trending Topics in Theory, more popularly known as the ST4 workshop. And as usual, we have two lectures today, followed by a short talk. So for the first lecture, let me welcome Arindam Bhattacharjee, who will continue talking about asymptotic symmetries and celestial holography. Arindam, ladies and gentlemen.
Today, so let me just recap what I was trying to do. So what I was trying to do is to show that the word identity of superrotation symmetry is nothing but subleading self-graviton theorem. Should I say it corresponds to okay, and the way I wrote this word identity was that I claimed that if superrotation is a physical symmetry of my system, then the charges of this symmetry should commute with the S matrix of my theory. And these charges were divided in two parts. So for instance, if you are defining the charges on Scri plus, I'll divide it in two parts, QH and QS, where this is the hard part and this is the soft part. And the hard part was the part that corresponded to the homogeneous action of the symmetry on my data, and its action, sorry, I've written QH plus, so QH plus acts on the out states. The action of it was written as acting on the out state. I may have written y del del z instead of the Lie derivative. The Lie derivative and the difference between these two is only apparent when you have spinning particles. And the soft part, we derived what the soft part of the charge should look like by because we knew that the soft part should generate this sort of a transformation. This the inhomogeneous part of the transformation was generated by the soft part, and that told us that the soft part looks like this. Up to some total derivative terms. Okay. So then we sort of put them back into this expression, and what we got is this, that QS plus S minus should be equal to okay. So this is the hard part of the charge acting on the S matrix. And notice now instead of writing y plus or y minus, I've just written y because I'm only using the diagonal subgroup of the BMS plus BMS minus group. And this is the word identity that I get from these theorems. Now what I want to do is that I want to write this identity in terms of modes so that it becomes clearer and it looks actually like a soft photon or graviton insertion rather. This works. Yeah. No, sorry. Sorry, thanks. Oh, so for non-spinning particles, this Lie derivative is just y del del z. And then for spinning particles, you will have an extra sort of Christopher symbol type of a piece that will be proportional to the spin of the particles. Okay. Okay. Yeah, so for the kind of theorem that you are going to prove, you can just consider y del del z. That should be fine. Yeah. No, because you can consider that except for the short particles, all the particles are scalars and stuff. Yeah, only one short particle. Okay. So now I want to sort of write this theorem in terms of the modes, and in order to do so, I can start from the usual. So let me just be a bit more precise. So any metric perturbation, right? So suppose my metric is like this. So H mu nu is the metric perturbation from the flat space. So I can write it in terms of modes. These alphas are the polarizations of the gravitons. Right? So that is just the mode expansion of the metric perturbation, where these are my creation and annihilation operators. So they satisfy this sort of a commutation relation that A dagger is. So if you take A alpha and A beta, then they have to be the same polarization. Then there has to be 2 omega q delta q minus q. Okay, some factors of 2 by q. Okay, so this is just the mode expansion of my metric perturbation, and then the radiative data CZZ that I had, I said in the Bondi expansion, this CZZ came as the linear in R piece of my HZZ, right? So I can define CZZ as limit R goes to infinity 1 over R times HZZ. Okay, so that will be my CZZ, and similarly CZ bar Z bar, I can define it the same way. And then I use the fact that at large R, these e to the power iq dot x, the spatial part of it is fluctuating really fast. So what that will tell me is that the saddle point of these integrals are basically when q and x point towards the same direction, and I use that fact, and using that I can write CZZ as, up to some normalizations which are not important right now. So this integral just boils down to just the integral over the energy. Okay, so I should probably mention that this q will be written as omega q times q hat. Okay, so that is my 4 vector, and using this here I'll ultimately find something of this sort. Okay, I'm writing the expression for C z bar, which is the same way. Okay, so this is the mode expansion of my CZZ. Now remember, the charge, the soft charge was proportional to the u integral, at least, of the soft charge was du u nzz bar, and what nzz bar, or the Bonding use, is nothing but a u derivative of czz bar, right? So you can do the same thing. You can just mode expand this, and you will see that you will get these minus I omega q's downstairs. So it will just look like this. Okay, so this is what my Bonding use looks like, and now what I can do is that I can define the modes of this, okay, which is just the Fourier modes of this Bonding use, which will just be defined like this. And then you can easily see that from this expression, this just boils down to some factors times epsilon plus z bar omega times a minus. Okay, so these are the modes of my News tensor. Now what I'll do next is this. I'll just take this. From this expression, you can see that if I take a u derivative of this, okay, the u derivative of this mode, or sorry, not u derivative, the omega derivative, then I'll get u nzz, right? So I'll get iu and then e to the power I omega u nz per z bar. Yes, and the omega goes to 0 limit of this is just u nzz integral that over u. Okay, so the omega goes to 0 limit of this quantity is what enters in my soft charge, right? So using this mode expansion that I have here, I can write that this, just call it nzz bar 1, which I define is just the u integral of that soft charge. Okay, and I can show that that is not so. When you apply the omega derivative here, you will apply. You can do it in similarly here in this part of that expression, and in this part of the expression, the omega derivative will act on this omega once, which will give you just 1, and then in the next one it will act on this a minus. So this will be just omega goes to 0 limit of 1 plus omega del omega acting on A minus. Okay, and this 1 plus omega del omega operator basically just projects out the 1 over omega pole that you would have anyway had at omega goes to 0 limit. So it just picks out the omega to the power 0 term of that when you take omega goes to 0 limit. Okay, so that is why I am calling it this calling it a sub-leading soft graviton. Does that make sense? Yeah, sure. Omega goes to 0 limit of this quantity, del omega of n omega zz. No, not omega, because I want this u nzz type of a term, right? My soft charge, the u integral of the soft charge is du u times nzz. So I want something of that sort there. So what I did is that I took a omega derivative that gave me a factor of u, and then what I did is that I take omega goes to 0 limit in both sides. Okay. In this side, it just gave me the u derivative of my so the u integral of my soft charge, and on that side, the omega goes to 0 limit after acting on del omega gives me something of this sort. Okay, and this in itself doesn't make sense. The only point is that if you have inserted this thing inside a correlator, then what it does is that what it says is that when omega goes to 0, there is a 1 over omega pole in the correlator, which is picked up by this, like which is cancelled by this operator, and then it picks the omega to the power 0 piece. Okay, so that is why this looks like a insertion of a subleading soft graviton.
The second term, omega del omega, will give me the subleading part.
This 1 plus omega del omega total. So you can just check this, that if you have this sort of an expression that, so what you know is that if you have some soft photon inserted with some correlator, right, some S matrix, say, okay, so then this has a 1 over omega piece, right, this is the Weinberg's soft graviton theorem, and then you have a omega to the power 0 piece, and then omega piece, and so on and so forth, right. So you apply 1 plus omega del omega, and you can show just this 1 over omega term gets cancelled out, right. And similarly, all the higher parts of omega also gets cancelled out, so you only pick up this piece. Okay, and this piece, because it's omega to the 0, you take omega goes to 0 limit, you just, okay, great. Okay, so that is why you can say that the QS plus piece is actually a soft part of the charge, because it actually does nothing but insert this subleading soft graviton theorem. Now let me just write what the subleading soft graviton theorem, the statement of it is. And again, I'll use this operator just to project out the 1 over omega piece, so that I don't have to write both the leading and subleading order soft graviton theorem. So I'll just write it like this, that okay. So this says if you have some states and you have inserted a soft graviton in the out state, okay, then that is equal to some S1 minus this, where S1 minus is just the k is just the label of the particle over pk dot q. Okay, So what this basically says is that at omega to the 0 order, if you have inserted a soft graviton, then at omega to the 0 order, you get this sort of a universal term, which is proportional to the angular momentum of the hard particles. Okay. And like I was saying yesterday, that all these momentas, because they are null momentas, and even you just saw when I was doing that integral also, that all these momentas can just be characterized by the z and z bar coordinates on the celestial sphere, right? Because if the moment you mention at which angle they enter, I can just write a unique null vector that corresponds to their momentum, right? So that's what I'm going to do. I'm going to parameterize all the momentas that you have, the momentas of the hard particle, just by the angle they come in. Okay. So Ek will be the energy of these particles. Okay, so these are the momentas of the hard particles. This is how I'm parameterizing the momentas of these hard particles. And similarly, I can write the polarization vector as, so both the plus and minus polarization vector as just a multiplication of these vectors, where these vectors will be something like del z. So the z and z bar components I'll just write. Okay, those are given by say 1/2. And similarly the minus components written as something like that. Okay. So if I parameterize my momentas like this and my polarization like this, so you can just evaluate what this term is. Okay. And then this term will look like some expression involving z's and z bars and e's. Remember, I have this angular momentum, which is just like p del p minus p del p, right? The antisymmetric part of it. So that will give me some del E k's also. Okay, so it will give me this full piece, and then you can show that this expression satisfies an equation of this sort. Okay, that if you multiply this with some polarization vector epsilon plus z bar, and then take a derivative, 3 derivatives of this expression, then you get this. Okay, where these delta functions come because whenever dz bar derivative acts on 1 over z, you get a delta function. Okay, so this is the expression for the subleading soft graviton part when I have parameterized my momentas and my polarization vectors in this way, and then I see that this expression admits, I mean, it solves, it follows this equation. Okay. The reason I am interested in it in this expression is that if you plug in these epsilons, oh,
Here you are marking out the case where all the external particles are massless, right?
all the external particles are massless, yes.
If I take some of the external particles, hard particles,
You can take them to be massive, but here the proof that I am doing here is just for the massless particle.
example.
It's an example, yes. Okay. So what you can do is that you take the first line of the soft theorem here, we call it equation 1. You multiply both sides of 1 with that term, say dz cube yz plus times epsilon z bar. You multiply both sides by this term and you integrate. Okay. So when you integrate, you see you can use this identity and you can write the whole thing as this is the left hand side, the integration okay, and the right hand side, because of these delta functions, become exactly like we had before, which is y del z at zk minus ek over 2 times dz zk till ek sum over k acting on out s, which is nothing but the statement of the word identity that you had for super rotation symmetry. Okay, so what this proves is that the subleading soft graviton theorem actually implies super rotation symmetry. Okay, and because super rotation generators follow Virasoro symmetry, we have seen, right? They are just the conformal Killing vectors of S2. So from there you can say that the S matrix in 4 dimensions, they have it has Virasoro symmetry. Okay, and as you can see, like at least for massless particles, at least the case that I did here, all of the particles are parameterized just by where they entered at z and z bar, which means just the it's enough just to point out the position of the particle at the celestial sphere S2, and that is enough. So from all this, it was motivated that if my S matrix has a Virasoro symmetry and and all the particles can be labeled just by their position at the celestial sphere, then maybe I can recast my full S matrix, full 4D S matrix in terms of just 2D CFTs. Okay. So this implies that my S matrix has Virasoro. Okay. So yeah, that concludes the proof, and that is sort of the motivation behind looking for 2D CFT that is dual to the S matrix, which I think now Partho will talk about. But I'll take any if you have any questions regarding this part. I just proved that the superrotation symmetry, the word identity for superrotation symmetry, and soft graviton theorem. I mean, no, I haven't proved they're same. What I proved is that if you have subletting soft graviton theorem, which is a true fact for any any gravity S matrix in 4 dimensions, then you have superrotation symmetry. Okay, then it follows superrotation word identity, and superrotation generators follow Virasoro symmetry. Right, so that proves that it has Virasoro symmetry.
This YZ plus, it is the vector fields of what?
Let's forget the plus part. Yeah, it's just YZ. It's the superrotation generators, which are both there at scry minus and scry plus. Right. The plus part was just to indicate that you are looking at the vector field near scry plus or scry minus. But when you take the diagonal subgroup, you just have YZ. DZYZ and ZK. ZK is just the position of the particle. Okay.
So when you incorporate massive particles,
right.
So your expression for PMU will
it will change. Yeah. So I have to change my parameterization in such a way that it incorporates massive particle. So that except for for massive particle, I'll have to find some p such that p square is -1, right? If I do that, then I can just take a overall mass factor out and sort of again reparameterize it in terms of just Z bar. I think Partho may talk about how to parameterize massive particles using, I mean, in this today. Okay, that's fine. But the point is that you can do it. Okay.
No, but I think for massive particle, like how can you associate with the symmetries near the null infinity? That's the
no, you cannot associate it with the symmetries near null infinity. But the point is that the subgraviton, the Virasoro symmetry of the S matrix is still there, right?
So what happens is that the parameter will still be a null infinity, but you have a bulk to so you have this bulk to boundary sort of this
Property.
function that
Yeah.
connects your parameter at null infinity to your parameter at hyperboloid near time like infinity. So once you get that bulk to boundary scalar function, then all these things follow from there.
the Virasoro will still work, or it is just the global?
No. You still have the full Virasoro symmetry. See, because subleading soft graviton theorem is true even if you have massive particles in your in and out state, right?
Yeah. So how to recast those in terms of this language?
You can still. I don't have those calculations yet, but I can show you. Like it's pretty standard. You can still do it. Yes.
So the S matrix also has super translation symmetry.
That's right. Yes, and that cause yeah.
How does the 2D safety capture that?
No, so what this basically says is that because you have a Virasoro symmetry, you have a 2D CFT, right? But you don't just have conformal symmetry there. You have more symmetries. So, for instance, super translation is one of those symmetries, right? So all those symmetries are extra symmetries that you impose on that 2D CFT. So it just doesn't have. So, for instance, I think the initial papers of Weinberg showed that this super translation sort of gives you a Kashmuri type of a symmetry that you have in your 2D CFT. Okay.
Super translation acts like a weight shifting
Operator.
sort of symmetry on the sphere. Like if there was some primary operator, and if you put this super translation like operator that generates super translation symmetry, you will get they will shift the weight.
Yeah.
By plus.
Even I think just translation you can also show that. Even pure translation shifts the weight. So those are sort of, so translation, the symmetry, that the fact that you have in 4D S matrix, you have a translation symmetry, it sort of becomes an emergent symmetry in the 2D CFT, right? Because in a 2D CFT, you don't expect that if you have some primary operators and you shift their weight, right, by some factor, say 1, you will still get the correlation, those two correlation functions will be related to each other. But we know they are related to each other in 4D because they are just, what I'm doing is just translation, right? So those will be some extra emergent symmetries that you have in the 2D CFT, whatever 2D CFT that you have.
Basically, this is sort of like a trade-off, right? So if you want to get a nice conformal symmetry,
that's exactly true.
Yeah, your super translations in this picture doesn't have like, it's very obscure form. It doesn't have very nice.
Right.
Like in 2D safety, it's not possible to incorporate super translation.
Right. Because you see, when you do Lorentz, when you talk about Lorentz symmetry and everything, right? In order to understand Lorentz symmetry, you have to go to a coordinate system and you have to fix an origin, right? And fixing an origin automatically breaks translation symmetry, right? So when you look at, when you find a basis, for instance, which I think this is Partho definitely going to talk about it. Okay. when you find a basis which has these Lorentz symmetry inbuilt in that basis, okay, you lose the information that there is a translation symmetry. So for instance, when you go to momentum basis, the momentum basis respects translation symmetry, but then all the fact that it has a Lorentz invariance and all this are suppressed in that basis, right? So that's the trade-off that Nishant is also talking about. Okay. Okay. Oh, so yeah, so the point is that what I'm trying to tell you is that S matrix has Virasoro symmetry, okay? What you're going to see in Partho's lecture, hopefully, that this, sorry. So I'm trying to like advertise his lectures a lot more. So what you're going to see is that in order to relate it to 2D symmetries, we are going to recast this S matrix as some, suppose there is an n-point S matrix. So I'm going to recast it as n-point correlators of the 2D CFT, okay? Some n-point primary operators. You will see that they change in the similar fashion and so on and so forth. So, yeah, and this transformation will, to go from S matrix to this n-point correlator language, you will need something like a Mellin transformation, okay? And then translation would basically mean, so Mellin transformation will have something like this, okay? You have omega, you have some, so you have some n-point scattering amplitude with some omega 2, something like that, and then you do a Mellin transform. I probably should not do these things, and then you recast this full thing as an n-point correlator. Awesome. This sort. And the point is that the effect of translation will be basically like changing these deltas, right? Because effect of translation is like del omega. That's like a time translation, right? So that will change the power of these omegas. Multiply by omega. So that will change these dimensions of these primaries in the 2D CFT language, okay? And if you say that your scattering amplitude has translation symmetry, for instance, that just means that in the CFT language, this correlator will be related to a correlator where this delta 1 is shifted by, say, -1. Okay? Yeah, sorry, +1. Okay? And that is an emergent symmetry in the 2D CFT, right? Because you don't, normally you don't expect this sort of a symmetry to be present in a generic 2D CFT. Okay? But this will be discussed in more detail in his talks. Definitely. Any other question?